Yeah, so this is more of a somewhat high-level introductory talk. So if you already know, if you're working on a ZK-VM, like this might not be for you, but if you want to build your own ZK-VM or like a bunch of them or just getting into it, like this is for you, so welcome. Right, so what do you need to build a ZK-VM? Basically, you only need two things. The first thing is you need a VM, and the second thing is a Stark engine, or at least that's how we do our ZK-VM. You can do it in different ways, but we're going to look at Starks today. So we're going to jump right into it, and we're going to build a, like maybe you can't even call it a VM, but we're going to see. So first level, my first ZK-VM. What do we need? Well, we need some sort of program memory, I guess, and we want to keep it as simple as possible for now. And so the program is read-only. It is stored in a dedicated memory part, and at any given address, there's either an instruction or possibly an argument to an instruction. Then the next thing we have is a processor, right, that is actually performing the computation. And this right here is the processor design that my first ZK-VM uses. These are all the registers we have available. So there's one that counts the number of cycles that have already happened, clock. There is an instruction pointer that points into program memory, instruction pointer IP. There's a register for the current instruction, the instruction that is about to be executed, CI. There's a register for the argument. And then in terms of memory, we're a little bit limited in that my first ZK-VM only has 2 memory cells and a memory pointer that selects which of the one is currently active. And that's it. So is it a VM? You know, you be the judge. Sorry. And we need an instruction set. Like, what are the instructions that this processor can execute? And there's only 4 of them. Increase, +1. Toggle the memory pointer, point to the other memory cell. Jump to a given address if, as an argument, if the currently pointed to memory cell is 0, and gracefully shut down the VM. Halt. That's it. Right, that was part 1, step 1, the VM. So now we need to figure out how to zk-ify that. And I mentioned that we're going to go with Starks. And so we need 2 very important ingredients. A, the algebraic execution tables, and B, the arithmetic intermediate representation. And once we have those, we just do the rest of the Stark. And that's not going to be part of this talk. There's links to resources at the end of the slides, and you should check them out if you're interested. It's really cool. Oh yeah, this is what the rest of the Stark looks like. It's, a little involved and not part of this talk. Right, okay, so here's an example program. It is in the program table. There's an address, the instruction, sometimes it's an argument. And yeah, that is our first AET. That's it right there. The somewhat more interesting one, I guess, is the one for the processor. So it is also a table, hence the name, and these are the registers as we have already seen, and we just initialize everything to 0, except where that doesn't make sense. And then we load the instructions into that. And now we start executing, and the processor just records every state it ever sees. So we execute instruction increment, and what happens is, well, the clock cycle increments by 1. The instruction pointer, this is not control flow, so it increments by 1. We load the next instructions, and the pointer to memory cell increments by 1. No big surprises there. And this is the next row in our table. And then we toggle the memory pointer, and we fill in the next row in our AET for the processor. And like that, we build up the entire processor table. And that is the AET. That's it. So that's step A done. That was rather fast. Let's move on to B, the AIR. Okay, the AIR goes hand in hand with the AAT, and the AIR makes sure that whatever lives in the AAT is consistent with the rules that we specify by virtue of the AIR. So these are what we want to have here is a bunch of multivariate polynomials that evaluate to 0 if and only if our AT is consistent with our spec, which we don't have, but we all kind of know what the VM is supposed to do. So there's 4 types of constraints. Initial, what's the value in the first row? Consistency, a row has to be consistent with itself. Transition, how do you move from one row to the next? And terminal, what's the last row? And most of them are pretty straightforward. For example, memory is initialized to 0. Consistency, the memory pointer can only point to one of the 2 existing memory cells, and it cannot have any other value. The transition constraints, those are usually the things where the meat is at. So that one is rather simple. Oh yeah, the notation here, the prime at clock, that means now we're comparing 2 rows in our AT. And the prime means we're looking at the second of those rows. So it's like whatever the next value of that register is supposed to be. So that one is pretty straightforward. But the instructions themselves, they are, a bit more complex. But not too much, because my first ZK-VM is pretty simple. So for example, if the current instruction is jump if 0, then the stuff that you would expect to happen should happen. For example, the instruction pointer is set to whatever the argument is. And memory consistency, we need to take care of that, right? The memory doesn't magically change. And then in my first ZK-VM, what I want is that you can only generate a valid proof if you actually shut down the VM gracefully. So you shouldn't be able to generate a proof if you crashed it, if you just ran out of instructions or anything like that. So the last instruction that you execute has to be halt. That's my requirement. Right, but these are not polynomials. Of course, I express them because it's convenient as Boolean logic. So how do we turn them into multivariate polynomials that evaluate to 0 if and only if the AT is consistent? Well, for most of them, that's really, really easy. For example, the first one, that's it. That's the polynomial. The second one, well, an OR is just multiplication in polynomial speak. So that's it. Likewise for the third. The fourth one is a little more tricky, but by turning it into disjunctive normal form, maybe applying some of De Morgan's laws, which I'm not going to run through. You have to turn this one into 4 polynomials, because there's a bunch of ands in there, and then you end up with this. And the last one, again, is pretty easy. Right, that's it. We have a consistent processor. Nice. I guess that means that my first ZK-VM is... Oh, right. No one's checking whether the program that we're executing is actually the one that the programmer wants us to execute, right? So we have a consistent processor, but memory loading, program loading, is not taken care of. And there's 2 challenges with this little triangle here. One is the processor executes the instructions in a different order than they're stored in program memory, right? We do have some sort of control flow. And secondly, it executes them more often than they are written down in the program table, because you can do loops. And so one neat way to get rid of this one little triangle is to just create 2 more. But luckily enough, now the problems are of smaller size. And by introducing this instruction table here, we can overcome the 2 problems that I just mentioned, like the multiplicity and the order. So I'm just going to throw the instruction table at you. This is it. We fill it in by first copying over the entire program thing. And we need to fill in, we have a new column here, next instruction or argument, which is just copied over from the program. And if the instruction is the last one, we just fill in a 0. And we fill in, additionally, the entire trace of the processor. You just copy it over. And then we sort that entire thing by address. And now we can very easily, in terms of AIR, talk about what does it mean for this guy to be correct. So here's our AIR for that table. There's no initial constraint, no consistency, no terminal constraints, because other tables are taking care of that. But the transition constraint, what we need to check that is that if the address stays the same, so does everything else, because the program is read-only. It cannot change throughout the run of the VM. And the second thing we want to check is that if the address changes, increments by 1, that's the only change that is allowed, then we sort of do a diagonal copy, because the next instruction should actually be the next instruction. And again, these are expressed as Boolean logic, right? But it's kind of straightforward to just turn them into multivariate polynomials. And now we have a consistent instruction table. That's pretty neat. So now we need to only take care of the links between tables. And for that, we modify the Stark engine, a bit. In that we are taking in verifier challenges. And we extend, using these verifier challenges, our algebraic execution tables to get, well, extended ATs, for lack of a better name. If you have one, hit me up. Let's see how that goes. I'm going to brush over it a little bit for reasons that I will say in just a minute. So by taking in verifier challenges, what we can do, now we have more columns that we can build. And these green things there, those are challenges by the verifier. And we can sort of build a random linear combination of every value that we have in our row. And that is, I call that a compressed row. And then you can feed that into, for example, in this case, a running product. And using that, if you feed that all the way through, you can make a permutation argument. Just like in Planck, for example. The P in Planck, right? That's the permutation. That's the permutation part. And the terminal down here, that is then the integral part of the permutation argument. And just like the AET and the AIR go hand in hand, so does the extended AET need a counterpart. And that is the RAP, the Randomized AIR with Preprocessing. There's not a lot of pre-processing going on in our case, but that's the term that is established. And it means, the specify box here is a partial evaluation of the AIR. Because we need to supply the actual values of the verifier challenges, partially evaluate our multivariate polynomials, and get new ones, which are then the RAP. And the reason I'm not talking about this in great detail is because Goethe will do that at 2 o'clock on the main stage, where she will talk about the power of multi-set checks in Stark-based VMs. So if you're interested in that part, and you should be, go check that out. And thanks to her, we now have solved our cross-table linking problems, and we actually have verifiable program loading. So that means that zero knowledge. We wanted to build a zero knowledge VM, I remember. Okay, so what can we do to turn this thing zero knowledge? Well, there's one easy trick. We just use a zero knowledge Stark, and we're set, right? Well, almost. Unfortunately, the terminals that we have computed for our XATs, they leak a little bit of information because they are sent to the verifier directly in the clear. And that's not going to fly in a zero knowledge protocol. And the way we get around this is that the prover supplies random initials. So now the running product starts at a random point, and if you want to check it, then you do not know anything right? Anything is explainable by that random value. This introduces a slight new problem in that how does the verifier know that the running product that was computed in two separate tables actually started at the same value? Because the prover now otherwise would have the opportunity to pick that initial value such that a actually incorrect running product or running evaluation or whatever you're using evaluates to the same thing, even though it shouldn't. And for that, we need a new type of constraint. So far, the 4 type of constraints that we've looked at, they are per table, right? Every table has some of them, potentially 0, but in principle. And the new type of constraint that we're introducing is one that links 2 tables. Or more if you want, but for us it's just 2. And so concretely, in this case, we want to make sure that in one table, the running product starts with the same value as in another table the running product starts with. And that's it. We have achieved zero knowledge. Awesome. Let's take stock. What is my first ZK-VM good for? Is it usable? Nah. Is it fast? How do you decrement again? It's not fast. Is it useful? Can you recursively verify it? How would you even go about that? Is it cool? It's a zero knowledge VM. Of course it's cool. So I give this 1 star out of 5. Let's try and see what the users actually want. Apparently, they want to somewhat communicate with the VM. So they want to have in and output. Let's tack that on. Level 2, ZK-VM with I/O. Back to the drawing board. 2 steps. First, build a VM, then make it ZK. So we already have a VM. This is it. That's the same thing you've seen before. Now we just say, well, there's a couple more instructions available to you now. Read write and read secret. Right, how does that change our Stark engine part? Well, this is what we have so far. And this is what we have now. We have a new table for input, a new table for output. That's it. All the other tools are already in place. So just like that, we've upgraded our VM. Of course, you need to take care of the air, but we're designing the things. Let the engineers take care of that. Okay, is it usable? Is it fast? Is it useful? I would say there is an argument to be made, and it might be somewhat involved, that yes, actually now it is useful. You still can't recursively verify that. And of course, it's still cool. So this gives it 2 star out of 5. I talked about recursive verification here twice now. What do we actually need for recursive verification? So one part is we need to read the proof, for which we need I/O, which we now have. Perfect. We need to do some fiat mirroring, for which we need hashing. We need to do some Fry verification, which means verifying Merkle tree membership, which means hashing. We need to check some commitments, which means checking Merkle tree membership, and which means hashing. And then we need to do some native field arithmetic, which our VM currently can't do, but that's easy to fix later. So apparently hashing is a really, really big part of it. Let's try and tackle that. Level 3, fast hash ZK-VM. Back to the drawing board. We need a VM. So let's use the one that we already have. And hashing just 2 memory cells is kind of like, that's not very useful. So I decided to give it more memory. It still lives in the processor because otherwise it gets a little more complex, and we want to focus on the hashing part. So now we have 16 memory cells available to us. And the instruction set has grown a little bit. We now have the instruction hash, just like that. And how does it work? How is it implemented? Well, first up, we're going to tack on a new table, the hash table. And this is where the hash coprocessor stores its intermediate values in the following way. This is if you want to compute just a single hash. Usually your hash functions are round-based. And for these kind of ZK-VMs, you really want to use something that is nice to arithmetize. I know that not everybody is doing that, but then you need to spend quite a lot of time engineering to make this really fast. If you use something like Rescue Prime or Poseidon, which is very nice to put into polynomials, then you have a somewhat easier time. Right, so this is somewhat like the processor in that you just record the result of every round of your hash function. And then, since this is an extended AT, you can compress the row just like before. And we want a different type of table linking argument here, but the principle is still the same. And unlike before, we don't want to prove a permutation of all the rows. I mean, it's not a permutation anyway, it's an evaluation. But we want to have this conditional. So most of the time, you just copy over the value, right? For feeding in, you can see this running evaluation as a sort of bus. So the processor sends 16 state elements to the coprocessor via this evaluation argument. Then it does its thing where it doesn't update the bus, and at the very end, it does update the bus again, which is the result of the hash, and sends it back to the processor. And that is it. We just designed a coprocessor and a bus between them, and now we have fast hashing. Let's take stock. I think it's still kind of difficult, but possibly you might be able to verify this thing recursively now just because you have hashing as a primitive, as a native instruction available. So 3 starks out of 5. All right, final level, Triton VM, which is the thing that I'm working on. I'm just going to brush over it, mention a few changes. Right, what else do we have in Triton VM, right? We have a coprocessor for bit fiddling. If you want to do a bitwise XOR, it's difficult to arithmetize unless you have a native coprocessor for it. I mean, there's other ways, but that's how we do it. We actually do have RAM, so you're not limited in the amount of memory that you can use. In fact, we also have a stack. We're not limited to 16 elements, but you can just keep pushing to it, popping from it, multiply 2 elements on it. But that's pretty straightforward, and I think almost everybody here could probably just get that working given the tools that you now have. And there's a jump stack also, so you can make functions calls. You can actually call return and not care about where you were being called from and all that stuff. And of course, the processor changes a bit, but not much. You have a few more registers, something that deals with the jump stack, something that deals with the op stack, something that deals with RAM, and a bunch more instructions because after all, we do want it to be usable and fast. So now this gets a perfect 5 out of 7 starks. Yeah, as I mentioned, there's some further reading if you want to brush up on your Stark or get a deep dive into it. Yeah, feel free to take a photo of that, or hopefully you can find them in the description below, whatever that means. And that's the talk. Thank you very much. Question time. Are there microphones?
Yes, we've got time for probably one question.
Only one question. I'm sorry about that.
Very nice talk. Just regarding hashing, just because you outsource it to a coprocessor does not mean it did its job correctly. How do you check that the computed was actually a hash? And doing that check, isn't it then slow, again slow, because you have to do it within your slow VM?
So the question is, how, just because you outsource your hash, I'm not sure the microphone was working, thus I'm repeating it. just because you're outsourcing the hash doesn't mean it's fast. And how do you check that it is actually a hash, and doesn't that make it slow again? So yes, you are right. You do need an AIR for the hash table, which does the checking. Are you actually computing the thing that you are supposed to compute? And isn't that slow? Well, that depends on the type of hash function that you're implementing. So there are these fairly recent arithmetic, algebraically optimized ciphers, AOC, or hash functions or whatever. And if you use one of those, then the polynomials with which you check that the hash was computed correctly, they're not of a very high degree, which is really all that matters in terms of performance of your zk-VM. So if you use one of those, then no, it's not super slow. I mean, you still have to do the start part for that, so you need to spend some time on it, some resources, but it's not super slow. If you want to do a traditional, like bitwise hash function, you're going to have a harder time. I know that there's people who are doing that, and I think they spend considerable amount of engineering on that, and I'm not sure what the performance is after that. Yeah.
All right, thank you very much.
Thank you.